Alright, let's go. So, we've got a real simple day today.
You do?
Yeah,
I thought we were doing 2 sections.
we are doing 2 sections.
Okay.
One section just does 2 proofs, the other section is just notation. And the notation stuff I won't test you on, it's just good for you to know just because when you go on and take another calculus class, chances are they'll most likely use Leibniz notation.
Are we not going to be using it very much for the rest of the class?
You'll see where it comes up with integrals, but you don't have to think about it the same way that you think about it here, so not really. Anyways, let's start with the proof. So the proof is, I think it's called the Cauchy mean value theorem. Let's see. Open up my book. See, my book's already open. Where are we? But it's basically the mean value theorem when you have 2 functions rather than 1 function. A quotient of functions, I should say. Let's see. And you almost prove it the exact same way that you prove the mean value theorem. So even the proof is relatively straightforward. Just let me make sure I get my initial conditions right. So yeah, it's called the Cauchy mean value theorem. This is theorem 4.23. So we have let f be a function from a closed interval a, b to r, and g be a function on the exact same interval to r. Let that and that be continuous and differentiable on the interval ab. Let that be continuous, comma, and differentiable on the open interval ab. That marker is garbage. Then there exists, we're going to call it some point. Oh, no, we need one more assumption. Because we're going to put g in the denominator, so we also need g to not be 0. Let me just roll this. Also, assume g prime of x is not equal to 0 for all x in the open interval ab, because that's where g is differentiable. Okay, now then there exists x naught in the open interval ab such that f prime at x naught over g prime at x naught is equal to f of b minus f of a all over g of b minus g of a. Okay. So, what is this essentially saying? It's saying that when you take the quotient of 2 functions, there exists a point such that the slope at that point is the average slope across the quotient of the 2 functions. Notice, what is the average slope of f of b? What's the average slope of f over this interval? It would have been f of b minus f of a over b minus a, right? That's f's average slope over that interval. Its rise over its run, its slope.
Okay.
And g, its average slope would have been g of b minus g of a over b minus a. Notice that when you take the quotient of these two, you just get that. So this is the quotient of their average slopes. So when you take the quotient of 2 functions, then there exists a point such that the derivative at that point is equal to, that's not the right way to say that. There exists a point such that the quotient of the derivatives at that point is equal to the average slope of the functions. So with the mean value theorem, we just did this at one point. we said there exists f prime of x naught such that this is true. Now when we're doing 2 at the same time, we're saying there exists f prime of x naught and g prime at the same point such that both these are true simultaneously. Almost. It's really the ratio. Does that make sense what we're proving?
Is there more of like a graphic representation that we can look at?
It's hard to graph ratio of 2 functions because you'd have f in one place, g in one place, and you divide f by g. So I'd completely butcher it. I don't have a good graphical representation, geometric interpretation of what this is saying, other than just respelling out exactly what it says. But one way that we think about it is we think about the regular mean value theorem as the Cauchy mean value theorem when g prime, or when g of x is just x. So if we let g of x equal just a function x, so let g of x equal just x, you with me? Then what does this say? This says f prime at x naught. What's g prime?
Just x.
What's g prime?
Oh, it's 1.
1. So g prime is always 1, so it's constant, doesn't matter what you do. So f prime of x naught over 1 is equal to f of b minus f of a. What's g of b?
Just b.
B. And what's g of a?
A.
A. So you can view the mean value theorem as a special case of the Cauchy mean value theorem. It's the Cauchy mean value theorem when the denominator is just a function x. Make sense? Okay, so let's actually prove this thing. And we prove it identical to how we proved the mean value theorem, almost. So we're going to use Rolle's theorem. You might not remember what Rolle's theorem is. That if a function's start and end are the same value, then the derivative was 0 somewhere between. So we're going to let h of x equal f of x minus m times g of x, exact same thing we did in proving the mean value theorem, where m is equal to this thing. You with me? So now with the special function, so we're doing f minus the average the function grows over how far we've gone is one way you can think about that. But in either case, we need to show h of a is equal to h of b, and then we can use Rolle's theorem. So we set up h of x this way. Step 2, prove that h of a is equal to h of b. Therefore, the derivative of this function is 0 somewhere in between, and where the derivative of this function is 0 is where this is true. And we're done. That's the big picture of what we're doing.
And you know that because of the mean value theorem?
No, we know that because of Rolle's theorem. Rolle's theorem says if f of a is equal to f of b, then the derivative was 0 somewhere in between. So we don't use the mean value theorem in this proof. We prove this the exact same way we proved the mean value theorem. It's just now we have a g of x here instead of just an x. Take your proof of the mean value theorem, replace g of x, or replace your x's with g of x's, and it's basically the exact same thing. Okay, 2. Observe that, all right, let's see, what is h of a equal to? H of a is equal to f of a minus m times g of a, right? With me so far? Now I'm going to plug in what we know m to be, and I'm going to get a common denominator at the exact same time. So m's this thing, so I'm going to multiply f of a by this term, and write the whole thing over g of b minus g of a. So see if you follow the algebra here. So I'm going to have f of a times, maybe we'll distribute this later, g of b minus g of a. So that was this term. Minus m was this thing. F of b minus f of a times g of a. All over now g of b minus g of a. You follow the algebra there? Anything weird?
I'm missing one for G of A. Didn't you have
So this f of a is here. I multiply this term, top and bottom, by g of b minus g of a. The numerator of m is here, and this g of a is here.
Okay.
So I rewrote this term the exact same way. This over this was just m. This term I just multiply top and bottom by that. So they have the same denominator. Good?
Sure.
Sure. Well, we can do it better if we need to.
No, it's
All right. Okay. So now what's this equal to? Distribute it out. We have f of a times g of b minus f of a times g of a minus f of b times g of a. And then minus and minus is going to make a plus f of a times g of a. All over g of b minus g of a. Right? And now two of my terms should cancel out. These two terms. So notice that this cancels out with this, and that leaves us with is equal to f of a times g of b, should be minus, there it is, minus f of b times g of a, all over g of b minus g of a. Right? And this is equal to h of b. If we expand it out, h of b, we get a similar thing, except for we'd have an f of b, g of b term that would cancel out and leave us with these terms. So I won't bother writing that one out as well. Make sense? So they're the same. So now we can use Rolle's theorem. So then, by Rolle's theorem, there exists x naught in the open interval AB such that f of x naught prime, the derivative at that point, not f, h. Sorry, this is h. We showed that h of a is equal to h of b. So by Rolle's theorem, there exists some point in the open interval AB such that the derivative at h is equal to 0. Right? Rolle's theorem, if your function starts, does whatever it does, but ends, and this have the same height, your function was 0 somewhere in between. This derivative was 0 somewhere in between. That's Rolle's theorem. So h prime of x naught is equal to 0, but h prime of x naught is also equal to what? What is h prime of x naught? How can we express it in terms of f and g? What is the derivative of h?
It's 0.
Well, it's 0 at this point, but what is the derivative of h in general?
It's not m, is it?
No. What's the derivative of f of x? You're overthinking it.
I'm overthinking, I'm sure.
What's the derivative of f of x?
How do we know?
It's f prime of x.
Oh, well, duh.
Well, duh. All right, minus, what's the derivative of g of x?
It's g prime of
G
x.
prime of x, and when you multiply it by a constant, it just multiplies the derivative by a constant, right? So, m times g prime of x. I mean, okay. It should be obvious that we're trying to somehow fish out f prime and g prime from this thing, right?
Okay.
Because ultimately, what am I trying to do? I'm trying to express f prime and g prime in terms of m. That's my ultimate goal. I'm saying when I express f prime and g prime in terms of m, they're just equal to m. So now I got this. So that gives me, I've got 0 now is at a particular point, x naught, sorry. So now I've got 0 is equal to this difference. So that gives me that f prime of x naught is equal to, move this to the other side of the equation, m times g prime of x naught, or divide both sides by g prime of x naught. How do I know that I can divide both sides by g prime of x naught?
Because g prime of x is not equal to 0.
Wonderful. G prime of x, we're guaranteed is not 0. Somewhere up here. G prime of x is not 0 on this interval. We know that x naught is a point in that interval, so we can divide by it and we don't have to worry about dividing by 0. And this is equal to n, which is exactly what we were after. That's it. Just the mean value theorem again, basically. Make sense? If you're getting stuck on this, I'd rewatch going through the mean value theorem and then look at this afterwards, and I think it'll make perfect sense. Because it's doing the exact same thing. Alright, and then the last one that we have to prove today isn't one that we're going to be using in this class. It's in preparation for a concept that comes up in Calc 2, and we're not going to be proving Calc 2 material. So if you take a Calc 2 class, then this concept will come up again, or if you continue with real analysis, it will come up again. And it's just something useful for approximating functions with polynomial functions.
Does the author go through Calc 2 later in the book?
Yeah.
We only do the first 6 chapters. He goes like all the way through the whole thing.
He derives all calculus, all the way through multivariable calculus. And yeah, you keep chugging away through it, you'd be a pro. Anyways, well, let me set up. Well, before we do it, there's something that's very useful to know while doing this proof. So I'm going to say, consider the function g of x equal to x minus x naught. Should we go more concrete than that? No, this is fine. Let's do it to like the 4. So g of x is equal to x minus x naught. X naught is just some number. Maybe we'll put an a there to help keep it clear. X naught minus a to the 4. Okay? Nice simple function. Let's look at g prime then at a. What's g prime of a?
0.
It's going to be 0, but let's write it out all the way through. So I bring down the 4. So I get 4 times x minus a to the 3, right?
Okay.
Maybe before I put an a there, let's just write g prime of x. And then we'll do the g prime of a's afterwards. So if we take the derivative of this thing, it's just this thing. Is that obvious, or should we write this out a little bit to help you see it if you're confused?
Just using the rule, right?
Yeah, we're using the chain rule now. The derivative of the outside times the derivative of the inside, so maybe times 1 to make it very explicit what we're doing there.
Yeah, that lost me a little bit.
Okay, so when you have a function like this, and it looks like it's a function inside of a function, you're confused on how to handle it, then you can do what we call a u substitution in calculus.
It doesn't really look like a function inside of a function.
Well, x minus a, there's a function, and then something to a power, there's a function.
Okay.
So, we could say we'll have f of x equal x minus a, and now we can say g, and let me use h now, I already used you over there, and we'll say h of x is equal to x to the 4, right? So now I can say g of x is equal to h of f of x. You with me there? So, g prime of x then, just using the chain rule, is equal to h prime of f of x times f prime of x. What is h prime of x? That's equal to 4x cubed. And what is f prime of x? 1.
Why?
What's the
Oh.
derivative of x? 1. What's the derivative of a constant?
0.
0. Add them up.
Yeah.
Remember, a derivative is just a limit. So you can do the limit of this plus the limit of this.
Sorry, this is probably a dumb question. How do we know that the limit of x is 1?
The derivative of x?
Yeah, the derivative.
Well, you can think about it in terms of the power rule if you want. X to the 1, take the derivative, is equal to 1 times x to the 0 is equal to 1 times 1 is equal to 1. One way to do it. Pictorially, graph y is equal to x. What's the slope of that function?
Okay, yeah.
Or you could always just take the bull by the horns and prove that the derivative of x is 1. What would that be? We want the limit as x approaches x naught of x minus x naught over x minus x naught. Bunch of different ways to think about it. So the derivative of x is 1, the derivative of a constant is 0. A derivative is just a limit. The limit of the sum is a sum of the limits. Left with 1. Make sense? Anything weird on this one? Okay, so plug it in now. So now this is equal to h prime, but not of x, h prime of f of x. So plug in f of x for x. Cubed times f prime of x. And now I'll write it all the way out. That's 4 times x minus a cubed times 1.
So couldn't we have used the power rule instead of using the chain rule?
We did use the power rule. We used the power rule twice, if that's how you want to think about it. We used the power rule here, and we used the power rule here.
Right, so what I'm wondering is why not just do that from the beginning with our g of x and go take the 4 down and subtract 1 from it.
That's what we did. The derivative of the outside times the derivative of the inside. Let me show you one that would have been a little bit different. If we would have had a 2 there, then that puts a 2 there, then this would have been a 2, because we would have had 2 there, so this would have been a 2. So this would have been a 2, and we'd still have a 2 there.
Okay.
So the derivative of the outside multiplied by the derivative of the inside. It's the chain rule.
That makes more sense.
Okay, yeah, should have gone to one where it wasn't just 1. Okay, but that's not the one I want you to care about now. That was all side stuff. So g of x is equal to x minus a, and we reduce it to the 4. So then g prime of x is equal to 4 times x minus a cubed, right? Now let's take the derivative again. Sometimes when we don't want to keep writing tick marks, another way to say that we're doing the derivative is we put the number of the derivative that we're taking in parentheses. So now the second derivative of x, or g double prime, same thing. What's the derivative of this thing now?
12 x minus a to the 2.
Yeah.
Exactly. Wonderful. Now let's take the derivative of that, the third derivative.
Where are we going with this? I'm missing the point.
You'll see it
It's 24
eventually.
times x.
Let me keep this actually as 4 times
3.
3. I think that'll help bring the point home.
Oh, okay.
Okay, so this one is
4 times 3 times 2.
4 times 3 times 2 times x minus a to the 1, right?
Mm-hmm.
And now the fourth derivative of x is equal to
It's 4 times 3 times 2 times 1.
just 4 times 3 times 2 times 1, because we're going to do it to the 0. The 0 just makes that whole thing 1. Or in other words, 4 factorial. Now, let's write out really quick what g of a is. What was g of a equal to? What do I get when I plug in a to this function?
1.
0.
0.
Right.
What about when I plug into g's first derivative?
Also zero?
Well, yeah.
0. What about when I do it to the second derivative?
0 all the way down.
0. The third derivative. 0. What about the fourth derivative?
Which no a in the fourth derivative.
So what is what do I get when I plug a into this function?
So 0. It's undefined.
A factorial? I don't know. 4 factorial?
4 factorial. This is just a constant function.
Oh.
What does this function look like?
Yeah, I guess it makes sense.
Right through the line 24. It's just a constant function. What's the value of the function here at a? Still 24. It's 24 everywhere. Okay. So this is just 4 factorial. Alright. So notice what kind of function we had there. We had a function whose value at a particular point was 0, and its first derivative was 0, and its second derivative was 0, and its third derivative was 0, but its fourth derivative, it gave us an actual value. And in general, if I would have let g of x equal x minus, this time I'm going to use x naught instead of a, don't get confused, that's just to prep you for the proof, to the n. So if I would have had g of x is equal to this thing, then g, one way we can think about just function g is when I put a 0 in there. That's just g, the 0th derivative.
Okay.
So that's another way to write g. But now I'm going to put a variable here. So notice that g's kth derivative at x naught is equal to 0 for all k, maybe put k in between two numbers, for all 0 less than or equal to k less than n, right?
Mm-hmm.
And k is a natural number, right?
Yeah.
I mean,
Yeah, good point. And that g's nth derivative at x naught is equal to n factorial.
Okay.
All that makes sense? Okay, so if all that makes good sense, now I think we'll be able to fly through this proof no problem.
That's only when there's not a constant in front of x, yeah? So there's no 2 there, essentially.
It has to be a particular function like g was.
Right, so what I'm saying is, it has to be in that form, there's no constant. So it's not g of x equals 2x minus x naught.
Correct. Yes. Okay, so now let's set up the proof. This is Theorem 4.24. Let's see. Let I be an open interval and let n be any natural number. And suppose the function f from I to R has n derivatives. And that at a point x naught in the open interval in I, the kth derivative of f at x naught is equal to 0 for 0 less than or equal to k less than n. Okay, So f is one of these weird functions that at a point x naught, it's always 0, always 0, always 0, until you finally take its nth derivative, then it's non-zero. Not necessarily n factorial, just non-zero. That's all we know about it. Let's see. Then, for each point x not equal to x naught, in I, there exists some other point z between x and x naught such that f of x is equal to the nth derivative at z over m factorial times x minus x naught to the n. Okay, quite a bit of a mouthful for this theorem, but it's actually not too bad to prove. So let's go over what we're saying here one more time, and then we'll prove it. So let I be an open interval, n is just a natural number, and suppose that f from an open interval to R has n derivatives, and that at some point x naught, this function is always 0 at that point for taking for the 0th derivative, the first, the second, the third, all the way up to but not including n. So it's a function very similar to that function g of x that we did that looked like this. It has similar properties to this function, although it's not necessarily a function like this. We just know it has these properties. You understand what we're starting with? Okay, so then we're going to prove that pick some point x that's not x naught. Then we're going to show that between these 2 points, there exists a z such that this is true. It looks kind of weird that way to see how we're using the mean value theorem, but let me rewrite this to the side and maybe it will help motivate how this is kind of like the mean value theorem we've been using. I'm missing an n factorial.
Underneath the half of n.
That should be in the denominator down here. N factorial, right? Did I do everything right? No, it should be there.
Should be on the other side.
It should be in the numerator.
Yeah.
The one that we took n derivatives of. Yeah, I think that's right. Okay.
Okay.
So, one, that derivative, or that denominator thing, this thing right here, we're going to let g of x equal x minus x naught to the n. And then we're going to just use the mean value theorem. Is he going to probably specify that? These are properties we already went over, but it won't hurt to restate it. Let g of x equal that, comma, and note that g to the k, g's kth derivative at x naught is equal to 0 for 0 less than or equal to k less than n. So g also has this nice property that f has. That it keeps spitting out zeros until the nth derivative, then we're not exactly sure what it spits out. Well, we know what g what it spits out. We know it spits out n factorial, right? Okay, so 2, we wrote down exactly what the Cauchy mean value theorem gives us, but maybe read that one more time. Suppose that the functions f on a closed interval a, b. Okay, let's get our closed interval first. So we know that x is not equal to x naught, right? So x to x naught is an interval, but we just don't know if it goes x to x naught or x naught to x. So without loss of generality, assume x, I don't know which way we want to do, greater than x naught?
Mhm.
Assume x is greater than x naught, and consider, the functions f, now on this closed interval, let's see, we did x naught first, x naught to x, and g on that closed interval, to r. So restrict the domain of f, and g restrict its domain now. In other words, f and g were initially defined on an open interval. The Cauchy mean value theorem works for two functions on a closed interval that are continuous on that interval and differentiable on the open part of their intervals, right?
Okay.
We know that g is differentiable everywhere and continuous everywhere, right? It's just a polynomial. And then f, it's given to us that it has n derivatives, and obviously if it's differentiable everywhere, it's continuous everywhere. Everywhere on that interval. So we now know that the Cauchy mean value theorem holds. Does that make sense? So 3. So then by the previous theorem, then there exists, we're going to call the first one, I guess, x sub 1. Then there exists x sub 1 in that interval. In the open interval, which one was first? X naught? X naught to x such that f prime of x1 over g prime of x1 is equal to what? What does the Cauchy mean value theorem give me? This is equal to,
We just proved it.
The same thing. But it's usually equal to.
I think that he wants to do the x's first, come to think of it. Because now that I'm looking at that, that seems weird.
Didn't we want to do that too?
So, I'm going to do this just because I think it reads a little bit nicer. So I'm going to do x to x naught,
I mean,
And
that's not how we did it.
x to x naught, and x to x naught. Anyways, okay. The Cauchy mean value theorem says that the derivative of this quotient is equal to f at the endpoint. Oh, you're right. We had it right before.
Yeah.
Wow. Should have listened. Alright. Flip it all. X naught. X naught. Should have kept writing before it's all wrong. Okay, f of x minus f of x naught over g of x minus g of x naught. Right?
Yeah.
Which is just equal to,
F of x over g of x.
right, why?
Because at every point,
Were you just reading out of the book?
What? No?
because at every other point it's 0, right?
Yeah, because these both evaluate to 0. Right?
Because of line 1?
Because, first off, look how g is defined. Where do we define g? Plug x naught into that, what do you get?
Okay.
0.
Oh.
Okay, and then look at how f is defined. F is defined such that at x naught it's always 0 as long as we've taken a kth derivative less than n. Here we're talking about its 0th derivative.
Yeah.
So you give us how both these are 0? Okay, which is equal to that. But notice that f prime of x1 over g prime of x1 is also equal to, we can't say that yet.
Same thing, yeah, we can.
Well, we can say it's equal to this. F prime of,
Isn't
how
that
do
the
I wanna
exact
say
same
that?
reason? Exact
well, we can write it as f prime of x minus f prime of x
same.
naught over g prime of x minus g prime of x naught.
How do we know that those?
Why can't we put the 1 in?
We just added 0 top and bottom.
Right, but how do we know those are 0 again?
We know for g, just because we know the function g. And then f prime of x naught, it's given to us that as long as we've taken less than the nth derivative, then at x naught it's equal to 0. But I didn't want to write this yet because we need to make reference to another point, x2. So maybe I'll just come and write down here as well. Then there exists x between, or there exists x1 in those points such that this is true. And then once again, since I also know that the derivative is well behaved, and for g the derivative is well behaved, using the Cauchy mean value theorem again, I also know that there exists x2 in x naught to x such that, this one I'm
X2 is
writing
in
backwards.
X naught to x1.
f prime of x2, g prime of x2, no, we can still use that whole interval. Should be fine.
Okay.
I wrote this one backwards from how I wrote up here. Okay, so up here, you follow the reasoning here, right? Cauchy mean value theorem. The derivative of a quotient is equal to this value. That's Cauchy mean value theorem. Rewrite this. That's the same as this.
Okay.
Good? Here, I accidentally did backwards. Okay. Cauchy mean value theorem says that there's some point such that the derivative is this. Oh, this is supposed to be second derivative. Sorry. That's probably confusing. I just did the same thing twice. Second derivative of this is equal to this. Because now we're taking the derivative of this function. Let me change the order that I wrote it so it follows exactly the same way the top line does, instead of backwards. Repeating the exact same process now. F second derivative at x2 over g second derivative at x2 is equal to f's first derivative, I guess I did that prime, at x minus f prime at x naught all over g prime at x minus g prime at x naught. But then that's a 0, that's a 0, which gives us f prime of x over g prime of x. Just using it twice.
So, okay. So basically f of x over g of x equals f double prime of x2 over g double prime of x2.
Yeah, how am I making my link back up there? Let's see, did I change the symbol from what he used?
Yeah.
F of x is equal to f of x over g of x which is the same thing as f of x minus f of x naught over g of x minus g of x naught, is equal to f prime of x1 over g prime of x1. Oh, to make it match back up, we have to restrict the domain. That's what you're saying that, yep. Okay, so down here, then we say now between x naught, how am I going to know now? That was x naught to x, we did that one right. X naught to x1, okay, x1 has to be between those two things, so now x1 has to be bigger than x naught, okay, that makes sense. So now if we put an x1 there, then that turns this one into an x1 and this one into an x1. And that turns this into an x1 and this into an x1. Okay, there we go. Thank you. That really makes the weight. So using the Cauchy mean value theorem up here, we got f prime of x1 over g prime of x1 was equal to f of x over g of x. Reapplying the Cauchy mean value theorem to this restricted domain again. So instead of going from x naught to x, we go from x naught to x1. x1 we know some point in between there, so it's still x naught to x1. So reapplying it to this new restricted domain, the Cauchy mean value theorem, we know that there exists some point called x2 such that the derivative of that point is equal to the quotient of the two functions that we're taking the derivative of. On this interval, we know that these two values on the right hand side are 0, so we just get this over this over this. Notice that that is exactly what we have over here. So this is still equal to f of x over g of x. And in general, we could repeat this process and we could say that there exists x sub n in x naught to x to the n minus 1 such that the nth minus 1 derivative at x sub n.
Isn't it just the nth derivative?
Yes, thank you. Because here's where we're taking our final one. Such that the nth derivative at x sub n over the nth derivative at x sub n, the nth derivative of g at x sub n, is equal to, exact same thing, the n minus 1 derivative at x sub n minus 1, the end point, minus the nth minus 1 derivative at the start point, all over g's nth minus 1 derivative at x to the n minus 1 minus g's nth minus 1 derivative at the point x naught, which is also still going to be f of x over g of x. Because every time we do it, it keeps still equaling f of x equals g of x. This ends up equaling the previous line equals this. If we did the third line, we would have gotten the same thing. If you do this all the way down, you keep getting the same thing. You good with that? Oh, I need to write one more step. Sorry. We know that these two are 0, so that leaves us just this, and then that's equal to f of x over g of x. Sorry. So this term's just going to be 0, so we're just left with nth minus 1 derivative of x to the n minus 1 all over g to the n minus 1's derivative at x sub n minus 1, and this is going to equal f of x over g of x. That's what it would look like if we carried it out. But now what we care about is that f of x over g of x is equal to this thing right here. So I'm using this, and I'm going to rewrite the equation. But now I'm going to rewrite it so that this thing is in the numerator of this. And maybe before I move it, what is this thing? We know the exact value of this function.
N factorial.
N factorial, perfect. So this right here is the same thing as n factorial. So I'm going to move the n factorial to the numerator of this, where you get n factorial times f of x over g of x, is what this is equal to. So that gives me that the nth derivative at x sub n is equal to n factorial times this all over g of x. Remember what g of x is though. X minus x naught to the n, which is what we were after.
Is it? Okay.
Xn is that point z. We just need to find a point z in the interval that made this true. Xn's in there. That is definitely in I. So Xn is the point such that the nth derivative of f at that point is equal to this.
So what is this theorem really saying?
So what this theorem is useful for is approximating complex functions, not complexes in complex numbers, approximating messy functions with polynomials. And that's what becomes useful for, something called a Taylor series expansion.
So is this how you would do a regression on a difficult polynomial? Like you would use this in some way? Is that how calculators do it?
Yes. Yes, for some functions. So, for example, if you want to write a sine function by hand, if you're programming a sine function, then you would use this Taylor series expansion, which is using this behind the scenes. I mean, when you prove the Taylor series expansion of the sine, you can see explicitly how you're using that right there. And you would use those polynomial approximations of sine, and you just expand out like the first 10 terms. You'd have to use infinitely many to perfectly capture the sine function, but there comes a point where you're within enough of a margin of error that you can now approximate it. So yeah, sine function on your calculator is using this. It's not calculating it. Well, we need to program the sine function in terms of things that we know how to manipulate. Everything in here, we know, if these are polynomials, we know how to manipulate. We know how to multiply numbers together. A sine function, what's a sine function doing? How do you figure that out? So, yeah, this is going to be one of those one-off theorems that you see it here and then we're never going to use it again in the class because we don't get that far. But it's still a pretty cool function. The fact that when we took the derivative at the point, we still got a function. When we took the second derivative at another point, we still got the function. Pretty cool that you can do that. After taking n derivatives, we're still expressing it in terms of the two functions that we started with. And all that happened is that n factorial in front. Anyways, so that's it for this material. Now we just got to cover Leibniz notation, and then we're done. And Leibniz notation for a derivative, probably easiest just to go all the way back and rethink about the derivative in terms of the slope, and then just rewrite it with Leibniz notation. So going way back to the beginning of the chapter, we started out with a picture of just some arbitrary function. Didn't really matter what was doing, something like that. And we picked a point, maybe expand this out some, and then we picked a point, we'll call it x, and this function right here, whatever it's doing, maybe not have it go so weird, just have it go off like that. This right here is the function f. I don't want to say f of x, because since I chose x to be a point, f of x is the height here. So we said, how might we, if we were a little bit more naive, like in an algebra class, try and figure out the slope of the function here? And we said, well, what we would do is we would probably take a point close to it, call it x naught, find the value at that point. So now the height here is f of x, and the height here is f of x naught. Let me switch those. We'll call this one x naught and x. We'll call this one x and x naught. So let's say we want to find the slope at x naught. How might we do it? We might pick some other point x that's close to x naught. And then we would say the slope at that point, we'll call it m. The slope at this point m should approximately be f of x minus f of x naught all over x minus x naught, right? We thought about this as a little triangle. And we're going to do the rise over the run. What's the rise? That's f of x minus f of x naught. And what's the run? That's x minus x naught. Right? Follow the algebra there? So another notation that's commonly used for these is our change in x, we use delta x, and our change in y, we use delta y. So we could also call this, that's delta x, or delta y over delta x. Our change in y over our change in x. Just notation. So now, our question, or now our derivative, we said, okay, we're going to take the limit of this thing now as x approaches x naught. Right? And that's how we got our derivative. Or another way to say that is we're going to take our limit as delta x approaches 0 of delta y over delta x.
Okay, why do you write it like that? It's delta x approaches 0 instead of x approaches x naught.
Delta x is x minus x naught.
Yeah, but like,
What is the limit as x approaches x naught?
0.
What happens to delta x? It approaches 0. So taking the limit of this as x approaches x naught and the limit as this as delta x approaches 0 is the same thing.
Right, I'm just wondering why. Is there a reason that you're writing it that way? It's
Yeah, because then we say this is equal to, with Leibniz notation, so before we said, up here we said this is equal to, we're going to call it f prime of x naught, right?
Mm-hmm.
Here we say we're going to call it dy dx, and this is Leibniz notation. So Leibniz notation, one of the reasons it's nice is because we think about it, we start with deltas, then when we take our limit, it gives us d's, and you get derivatives now. So dy dx is a derivative of y with respect to x is the way that you read that. This is saying the exact same thing. So instead of f prime of x, we say the derivative of y with respect to x, or dy dx. And this is just a symbol. Dy dx is the derivative of y with respect to x, where y is your function. So for this notation to make sense, then we need this function. You can think about it as f of x, or you can think about it as a function of y in terms of x. Right? So I'm going to rewrite this all now, just focusing on the Leibniz notation. Forget our old notation, and you'll see what I mean, hopefully. So go back, we'll still have x naught and x, but now we'll call this point y naught, and we'll call this point y. So this is delta x, this is delta y, or y minus y naught. So we want the limit as x approaches x naught of y minus y naught over x minus x naught. This is the same thing as the limit as delta x approaches 0 of delta y over delta x, which we're going to use the symbol dy dx to denote, where y is equal to f of x in general, right? Y is the height of the function. You're used to writing y equals f of x. So y is typically some function in terms of x. Make sense?
Okay.
So let's do one thinking about it this new way. So if I say y is equal to the function 3x squared, one that we know how to do, then what is dy dx equal to? That's what we're looking for, okay? So we're looking for, let me write this another way, we're looking for the derivative with respect to x. One way that you might see it is written this way. If we're going to put the y in, sometimes we, instead of putting it there, we put it here. 3x squared, but you could have also just done the derivative of 3x squared if you wanted like this. Either notation is acceptable. Dy dx, which is equal to, now we'll calculate it. Dy dx, it's equal to this limit. That is equal to the limit as delta x approaches 0 of, Should have made this clearer before I did it. Another way that we can specify y naught is equal to f of x naught. But now y is equal to, we could say y is equal to f of x, but that's also going to be the same thing as f of x naught plus delta x, is actually the way we think about it. Y is the value you get for x when you change it a little bit, is another way that we say that. It's just exactly what that y point is. That y is this.
Y.
X naught plus delta x. Yeah, I should have written it down this way. This is x plus a little bit, delta x. And this is, y at that point is f of x naught plus delta x. That is the y associated with it. Okay, follow that?
Yeah.
Okay, so now this is equal to the limit as delta x approaches 0 of f of x plus a little bit minus f of x all over delta x. With me? That's just using the exact definition. You're used to this definition, the limit as x approaches x naught of f of x minus f of x naught all over x minus x naught. This is the exact same thing. Where delta x here is equal to x minus x naught. So look at, let's take, notice that delta x is equal to x minus x naught. Let's rewrite this, making that substitution. So this is equal to the limit. Well, if delta x approaches 0, using the fact that x is equal to x minus x naught, that's the same thing as x approaches x naught. Plugging in delta x, we get x plus, that is weird. X
To the x naught.
naught plus delta x.
Also in your f of x.
And f of x naught. Okay. There we go. That's better. So now when we plug that in, we say this is going to be f of, plug that in, we get x minus x naught plus x naught gives me f of x minus, that's still just f of x naught, all over, and now delta x is x minus x naught. So they're the exact same thing, just a different way of thinking about it. Is that weird?
Not super weird. No.
It's not weird.
Okay. So this is the definition that we use when we're using Leibniz, this is the definition that we use when we use Leibniz notation. Now, since we don't have an x already, we don't need an x naught, so the x now acts how the x naught used to. Because we're saying the derivative at the point x, instead of at the point x naught. Make sense?
Yeah.
So now, let's write this out for this particular function. What is f of x plus delta x? So that's going to be 3 times x plus delta x. We're going to be taking the limit of this though, so let me write my limit first. The limit as delta x approaches 0 of, we have, plug in x plus delta x into this function, we get 3 times x plus delta x.
Wait, what? I think
Squared.
that was wrong.
I'm plugging x plus delta x into our actual function now. My function is 3x squared. This is what I'm taking the derivative of. So this is just what it is in general. Now I need to take my actual derivative of this function. What do I get when I plug x plus delta x into this function? I get 3 of that thing squared. 3 of that thing squared.
Okay.
Is something weird?
Yeah. I don't know why.
So if f of x is equal to 3x squared, then f of a is equal to 3a squared, and f of anything, x plus delta x, is equal to 3 of that thing squared.
Okay.
So we're just plugging that in for x into this function.
Okay.
Does that make sense now?
Yeah.
Okay, so we have f of x plus delta x minus f of x all over delta x. Now notice that the reason that we can't just take this limit is otherwise we'd be dividing by 0. So you have the same goal with this limit that you have with every limit. Try to make so I'm not dividing by 0 anymore. Make sense? So I need to get that delta x out of the denominator so I can evaluate this limit. And you do it the exact same way you did with all the other ones. We're going to expand this out. We're going to see one term cancels out with this. The rest of the terms have delta x's in them. Cancel out delta x's, and we can take our limit. Delta x approaches 0 of, expand this thing out. When I expand this term out, I'm going to get x squared plus 2x delta x plus delta x squared. That's what I get if I just expanded this out, and now I just need to multiply each of those by 3.
Okay.
So we get a 3x squared canceled out with this one, so I won't bother with the x squared, plus 3 times 2x delta x gives me 6x delta x, plus 3 delta x squared. So this term canceled with 3 times this term, leaving me with these two terms times 3 right there. You follow that over delta x? Now we can cancel out the delta x from the numerator and the denominator. So this is equal to the limit as delta x approaches 0 of 6x. 6x, we cancel out 1 delta x from that term, plus 3x delta x. Notice that you still have 1 delta x in this term, because we can only cancel out one of them.
That's only
What?
3 delta x, right? Not 3 x delta x.
Okay, let me write this one more way.
You
I'm
can
in.
cancel it out twice?
I'm going to factor out a delta x from the numerator. Let's say it that way first.
Okay, that
Right.
makes more sense.
So delta x times 6x minus, or plus 3 delta x, all over delta x. Now they cancel out, and so we get the limit as delta x approaches 0 of, those cancel out, so of 6x plus 3 delta x. Okay, now we can take our limit. Obviously, as delta x approaches 0, this term goes to 0, and we're left with just 6x.
Oh, okay.
Which is obviously what we knew the derivative was,
So much work.
just taking the derivative. It's so much work because we're doing it using the definition. Our first derivatives were this much work. I mean, would you like to see this same derivative doing it the way we did before?
It's the same thing.
Yeah, it's almost identical. So if we would have done this derivative with our definition before we knew the chain rule. This is just using the definition. We proved the chain rule with the definition. Or we proved not the chain rule, but the power rule with the definition. But if we were doing it with our old definition of a derivative, then we would say it's the limit as x approaches x naught of f of x minus f of x naught all over x minus x naught. And this is equal to the limit as x approaches x naught. Now let's plug in our actual function. This was a function we were taking the derivative of. So that's 3x squared. I lost it. Okay, yeah, 3x squared, just that. Minus 3x naught squared all over x minus x naught. Right? Just using our old way of thinking about it. Now, we can't take the derivative because otherwise we'd be dividing by 0. So I'm going to factor out a 3 from the numerator. I'm going to factor a 3 out from the numerator. Maybe do that first before I factor this term, just in case. Okay, now that's equal to the limit as x approaches x naught of, notice this is a difference of squares, so I can write that as x plus x naught times x minus x naught. So that's 3x plus x naught times x minus x naught all over x minus x naught. Okay, the denominator cancels out with this term. We're left with 3x plus x naught, which gives us 3x plus 3x naught. Now we take the limit as x approaches x naught, which obviously leaves us with 6x naught. You follow that? Was that too much algebra at the end?
X, right?
X naught. Here we're taking the limit as x approaches x naught. So the only weird difference in the notation going back and forth between one of them, This notation uses x the same way that this notation uses x naught.
Right,
So this is the
Why
derivative
would you
at
stick with
x,
that?
this is the derivative at x naught. Huh? So one's using Leibniz notation, the other is using the notation we've been used to. Good? So let's express some other things in terms of Leibniz notation. One of the reasons that Leibniz notation is so nice is sometimes we can think about that dy dx as a ratio. Very useful for something called implicit differentiation, which we won't do in this class, but chances are when you go take a regular calculus class, you'll see this notation far more than just f prime notation because of how useful it is. So now let's think about an inverse function. What would its derivative be? And we won't prove anything, we'll just give you the intuition and show you why Leibniz notation is so useful. So we know that if I want to do the derivative of f inverse prime at some point y naught, then that's equal to 1 over f prime at x naught. You remember that? That's just a derivative. This is an inverse symbol. The derivative of the inverse is 1 over the derivative of the initial function. Well, this is the same thing as asking what's the derivative of x with respect to y, instead of the derivative of y with respect to x using Leibniz notation. And we can think about these as, even though it's technically not correct to do so, it turns out in a lot of cases you can almost treat these things like they're just variables divided by each other. And so we can rewrite this as 1 over dy dx. So if you express x as a function in terms of y, which is what you do when you write the inverse function, right? Then if you want the derivative of x with respect to y, that's the same thing as 1 over the derivative of y with respect to x, which is exactly what that's saying.
We don't actually treat those as actual variables, right?
They are not variables. This is just a symbol and this is just a symbol. It turns out that there's a lot of circumstances with Leibniz notation where you can treat them that way, and it works.
But you're not technically supposed to because it's not correct to do that, right?
How can I say this?
I know what you're saying.
There are certain, well, you say technically you're not supposed to.
Like it works out, but with Leibniz notation, those aren't written as actual variables. Like dx is not a variable.
dx is not a variable, but we treat it like it's a variable all the time because it's very useful to do so.
Right.
So, yeah, when you're going through it, you need to understand the limitations of when you can and you can't. But the fact that there's so many circumstances where you can just treat that thing like a variable is extremely useful in solving problems. And so that's one of the reasons that that notation is so absolutely useful. So for example, I'll come up with one. This is called implicit differentiation, but I'll show you something. We'll do y squared. I don't know if this is going to come out hairy. It's sometimes hard to come up with a problem on the fly and have it work out. Is equal to 3y plus 6x cubed. Okay, we've got some crazy function there, and I want to find the derivative of y with respect to x. Now that looks like a nightmare, right? But it turns out I can just rethink using well, here's one way I'll say it. What's the derivative of y? Let's just do this. What's the derivative of y?
2y.
Or of this term, thank you. It's 2y. But then we know we still need to take the derivative of whatever the y term is, so we put the dy there. And then we say plus, what's the derivative of 2x? 2. But we still need to take our derivative of x. Oh, sorry, no. We're doing, stop. That's my bad. This is my bad, not your bad. We know, sorry, look at our definition. The derivative of y is dy dx, sorry. The derivative of y is dy dx. So when we take y and we take its derivative, it's equal to that. Y prime is equal to dy dx. That's one way to say it. Okay. So when we take the derivative of this, we get 2y just like you said. But now we need to do, we're basically using the chain rule. Take the derivative of the outside multiplied by the derivative of the inside, which is dy dx. Okay. plus 2 is just the derivative of x, right?
I missed what you did.
The derivative of this term, of y squared, we're thinking about y is some function in terms of x. It's possible for us to get y as a function in terms of x, right? So, what's the derivative of y squared?
It's 2y.
It's the derivative of the outside, 2y, times the derivative of the inside.
What's the inside?
Y is a function in terms of x.
Okay.
I don't know what it is, but let's say that it turns out y is equal to x cubed minus 2x. So I really have x cubed minus 2x squared.
Okay.
Y is some function, I don't know what it is, in terms of x. So I have some function squared.
That helps us say that they're functions and not just,
Yeah, y is a function in terms of x. We're thinking about y is a function in terms of x. You with me?
Yeah.
It's possible for me to take this and solve for y and get y as a function in terms of x. So y is some function in terms of x. So when I take the derivative, it's going to be 2 times the inside, or the derivative of the outside times the derivative of the inside. Just this plain
Why?
old.
How is that the derivative of the inside?
By definition, dy dx is a derivative of y. It's the derivative of this thing, whatever it is. We don't know.
Yeah, so aren't you...
We're going to figure out what that thing is.
What I'm saying is, that is 2y plus or minus something, right?
It's 2y times something.
What I'm saying is, so dy over dx is...
A derivative. That's the exact same thing as f prime of x.
Yeah, but isn't 2y part of that derivative?
Now, if I were to have, so let's see. So if I were to say that h of x is equal to f of x squared, and I want to know, okay, what's the derivative now of h of x? Well, that would be equal to the derivative of the outside, 2 times f of x to the 1 now, times the derivative of the inside, f prime of x. That's a 1, not a prime. So we'll just leave it off. Now, chain rule very explicitly. If I have h of x is equal to a function g of f of x, then h prime of x is equal to, using the chain rule, it's g prime of f of x times f prime of x. Yes? Okay, so now, what happens if g of x is actually equal to the function x squared? G prime of x is equal to 2x. So, h prime of x, in that specific case, where g is equal to this, gives us 2 f of x times f prime of x still. Because we don't know what the f is, we just know what the g is. Right? That's exactly what I've written here.
Okay.
Make sense now?
Yeah.
Alright, and now the derivative of 2x is just 2, is equal to, probably shouldn't have y's on both sides, we'll be fine, is equal to, what's the derivative of 3y?
3.
Almost. 3 dy dx.
Right, that's what I meant.
Plus, what's the derivative of this thing?
18x.
Squared. Right? Wonderful. And now we can just treat the dy dx like it's a variable and solve for it. And that gives us what the derivative is.
Huh?
That's crazy. That is so easy.
So now I can move this term to this side, this term to the other side. So I'm going to put all my dy dx's over here and all my other terms over there. So I have 2y dy dx minus 3 dy dx is equal to 18x squared plus 2, right? Minus 2. Minus 2 So now factor dy dx out both those terms. We get dy dx times 2y minus 3 is equal to 18x squared minus 2. Now divide both sides by 2y minus 3. And I get dy dx is equal to 18x squared minus 2 all over 2y minus 3.
But what's your function? What's the derivative? The derivative of?
It's the derivative of some function y, whatever you get if you solve this thing for y. We don't even know what y is, and yet we still know what the derivative is. Now, if we need our derivative in terms of x, then we're going to have to substitute. So we'd have to solve this for y, substitute that in here, and then we'd have this purely in terms of x, if we need that. But sometimes you don't need that. Now, we could have done the exact same thing, but now this time, let's say I wanted to think about this as, so I know that I could take this thing and now I could solve it and get x in terms of y. Right? I could write x is equal to a function and express it in terms of y.
So that's how you find the inverse?
Yeah, which would be the inverse of y, is what the x would be. But the point is now I could just take the derivative, but now I'm looking for the derivative of x with respect to y. And that would have been 2 times y. Now we treat our y's like our x's and our x's like our y. Plus 2 times dx dy is equal to 3 plus 18x squared dx dy.
Okay, can we do that one too?
Yeah. Now I'm treating my y's like my x's and my x's like my y's.
Right.
What's the derivative of x squared? 2x.
Okay.
Huh?
Okay.
We're treating our y's like x's and our x's like y's. Okay. What's the derivative of 2y? 2y prime.
Okay.
Is equal to
How did we
3.
do that?
Huh?
How did we do that one? Again. Use the chain rule?
The derivative of 2 times f prime, or 2f of x, is equal to 2, the derivative of this. How should I say the derivative? See, with Leibniz notation, it's really easy to say what we're after. We're after d with respect to x of this thing is equal to 2f prime of x. A derivative is just a limit, right? A limit of a product is a product of the limits. Take the limit of this, that's just 2. Take the limit of this, that's f prime of x. Redo their product. Or, if that's still not clicking, then let's just write it out to make it very obvious. The limit as x approaches x naught of 2 times f of x minus 2 times f of x naught all over x minus x naught is equal to, factor the 2 all the way out the limit, 2 times the limit as x approaches x naught of f of x minus f of x naught all over x minus x naught, which is equal to 2 times f prime of x naught. And then you could always think about it in terms of the chain rule if you want. Or, sorry, not the chain rule, but, yeah, the chain rule. The derivative of the outside multiplied by the derivative of the inside.
So you're saying dx over dy is just the derivative?
It's the derivative of x with respect to y.
Right. But it's just a derivative. It's a derivative of a function?
Let me write this out one more way to be super explicit. I should have done this to begin with, the first way that we wrote it,
I mean, it makes sense.
to help everything make sense. So let's rewrite it the way we did the first time. I'm taking the derivative with respect to x. So let's go back to taking the derivative of this with respect to x. So for the first one, what did we get?
2 times dy over dx.
2y times dy dx, right?
Yeah.
Plus, now I'm taking the derivative of this with respect to x. What do I get?
Oh, so you're doing both?
What does that mean?
Oh, just 2.
The derivative of something with respect to?
I'm taking the derivative of 2x with respect to x. So I'm treating x like the variable I'm differentiating on. It's just 2, right?
Yes.
If it is just 2, if we were being very explicit, we'd say it's 2 times the derivative of the inside, 2 times dx dx. Well, dx dx is just 1, so 2. And this is equal to 3 times dy dx plus 18 x squared times dx dx. And dx dx, again, is just 1.
Can you show me how dx dx is just 1? Okay, but it's not an actual fraction.
Let's see. Dx dx, by definition, is equal to the limit as delta x approaches 0 of delta x over delta x,
Okay,
which is 1.
it's just 1.
So taking the derivative with respect to x of each of these things, then all our x terms just have a dx dx term. Make sense? Which are just going to be 1. So that's the same thing as 2y dy dx, which is what we had before, plus 2 is equal to 3 times dy dx plus 18x squared. Because the dx dx is just 1, the dx dx is just 1. dy dx, that's not necessarily 1, but dx dx is always just 1.
So doing this, could you technically like differentiate conic sections?
You can differentiate anything.
I thought, well, conic sections aren't technically functions, are they?
Aren't technically functions.
If you have a circle and then like an ellipsis.
Oh, yeah, you need to break it up into its 2 cases.
Okay.
I mean, you could probably still just do it anyways. I don't know if we'll run into a problem. So, let's think. If we have y squared plus x squared is equal to 1, we'll think about just a circle. Yeah, I think we'll be fine. We'll just get 2 solutions. So yeah, we'll be fine. So now if I want to find the derivative of y with respect to x, if I want to find the slope on the circle at any point, take the derivative of this, what do we get? We get 2 times y times dy dx plus 2x times dx dx is equal to 1, or in other words, dy dx is equal to 1 minus 2x over 2y. Oh, but that implies we can solve it for y. Y is going to have 2 solutions. So you'd have to break it up into its 2 cases. Because for any x you have to give me on a circle, there's 2 y points associated with it. So you probably want to break it up into the top half of the circle and the bottom half of the circle. So yeah, since you have to express it in terms of y. Because what is y? We can just write it real quick.
Aren't there would also be
Y squared is equal to 1 minus x squared, so y is equal to plus or minus the square root of 1 minus x squared.
Are there points at which that's undefined? I mean our other function, the dy dx.
This?
Yeah.
Well, notice that our function is only defined on an interval from -1 to 1. Because I can't take a square root of a negative number.
A closed interval, right?
Closed interval, yeah. So yeah, this is going to be defined just fine on a closed interval. Oh, no, it's not. Because where y is 0, we're not going to be defined. Which, where y is 0 on a circle is where you have infinite slope.
Infinite slope.
Yeah, if you plot a circle, where is y0? y0 here and here. What's the slope at those points? Well, its tangent line is straight up.
Right.
What's the slope of a straight up line?
That's undefined.
Infinite. Whatever you want to call it. So that's the one. Those are the points you gotta watch out for.
Yeah, that's what I was thinking.
Yep. But anywhere else, it should give you the slope just fine.
Right.
So for example, if we plug in where y is 1 and x is 0, then the derivative better be 0. So if we plug in 1 for y and 0 for x,
Then you get 1 hand.
what did we do wrong? dy dx.
Well,
that some
You think it
simple
is
algebra
somehow?
error? That it should come out to 0.
It is probably an algebra error. It's probably that.
Y
last
squared plus
substitute.
x squared is equal to 1. That should be fine.
Why does it need to come out to 0?
The slope at this point is 0 for sure.
Okay, so wait, is the derivative the same thing as the slope?
Yes.
Oh.
What am I missing? One minus 2x. Yeah, I'm getting 1 over 1. Or 1 over 2, right?
Yeah. Oh, wait, y wouldn't be 0.
No. At this point, y would be 1.
Oh, and x would be 0? Oh, okay.
Yeah. I am missing something very obvious.
Well, it does say dy over dx. I don't know if that does anything.
That's just telling us what the derivative is.
Yeah, but it's the y over x.
So I should be able to plug in my points and get the slope. What the heck am I missing? So if we think about just a positive case, substituting in y here, we get 2 over the square root of 1 minus x squared. Sorry, this is getting driving crazy if I don't figure out what's going on. Alright, so let's just do it this way. So I know that y is equal to, solving this for y, and we'll only look at the top case, we get 1 minus the square root of x squared, right? And we can think about that as f of x if that helps you better. But that's the same thing as y is equal to 1 minus x squared. Now the square root is 1/2. Okay. So now, using my chain rule, y is equal to 1/2 times 1 minus x squared to the negative 1/2, derivative of the outside. Bring down the 1/2 and minus 1. Times the derivative of the inside is 2x. Right?
Is it?
Yeah, the derivative, oh, minus 2x, thank you. Yeah, the derivative of the inside of this thing, derivative of 1 is 0, derivative of negative x squared is negative 2x. So that's my chain rule. And now, what do we get? We get y is equal to, the negative exponent brings it down under, so we get 1 over 2 square roots of 1 minus x squared times negative 2x. Negative 2, oh, negative, that's what we have.
Oh,
But those are
but
multiplied.
it's times.
Ooh, but it's times.
Then it'll be 1 times 0.
So yeah, so that
So it's not 1 minus 2x, it's 1 times 2.
minus 2x, which is equal to negative 2x over 2 square root 1 minus x squared.
Which makes more sense. Because that would be 0.
When we differentiate both sides, the derivative of 1 is 0. We were missing something very obvious. I knew it. Something stupid obvious. The derivative of 1 is 0. Okay. Wow.
Right, okay.
Good thing we didn't record that, huh?
It's not recorded.
It is.
No, it is. That was a joke.
I'm like, what? I'm gonna be screwed.
Alright. So I don't know, that gives you a good feel for Leibniz notation. You can look at the examples the book goes over. We didn't go over the same stuff that they went over, so read their explanations. I think they just try to make the theorems that we've already proved use intuitive sense.
So what is the difference between dy dx and dx dy? One is the inverse function of the other.
Right. dy dx means y is a function in terms of x, and we're taking the derivative that way.
Oh, okay.
Dx dy means we're now viewing it as x is a function in terms of y, and we're taking the derivative that way. So we're taking the derivative of the function x with respect to its variable y. We're taking the derivative of the function y with respect to its variable x. So that's why that terminology is often used. The derivative of y with respect to x. Treat this like the dependent variable and this like the independent variable. That's ways of saying the same thing. Make sense? Okay, that's it. Test next week.